Hello guys, this is Prime Concept. Now we want to look at arrangement of capacitors in this video. In our previous video, we established the concept of a capacitor. We explained what a capacitor is. We talked about what a capacitor depends on. So in this video, we're going to consider the arrangement of capacitors. Now, what do we mean and why is the arrangement of capacitor very important to us? It's very important because capacitors in the market are produced in different sizes. Now, say you're working on a particular electronic circuit and you need a capacitor that has a capacitance of 3 farad. And then you go to the market, and what you can find in the market is 1 farad and 2 farad. Then it means that if you have to work with a 3 farad capacitance, then you have to find a way to combine the 1 and the 2 farad capacitors so that it can give you a value of 3. Now, this method of combining them to get a value, an equivalent value that you want, is what we call the arrangement of capacitors. Now, we have different arrangement for capacitors, but in this video, we're going to consider just 2 arrangements of capacitors, right? Now, please, if you have been following my videos and you are getting values from my videos, do well to hit the subscribe button. Subscription is actually free. It doesn't cost your money, so do well to subscribe so that you can be the first to be notified when I upload new videos. Like my videos, comment, and share with your friends so that they can also benefit like you. Thanks. Now let's go to the business. Now we're talking about arrangement of capacitors. We're going to consider 2 kinds of arrangement in this case. So number 1 we want to consider is the series arrangement. Series arrangement. So capacitors are arranged in series. When you connect them, the end of one to the start of the other. Or you can say capacitors are connected in series when you connect them head to tail. Now let's say we have 2 capacitors and I want to connect them in series. What I would simply do is I have this. This is one capacitor, I would call it C1. And then I have another one, I'll call it C2. So I have 2 capacitors. This is the end or the head of this one, and then this is the tail. This is the head, and this is the tail. Now, if I have 2 capacitors and I want to connect them in series, what I would simply do is I will connect the head of one to the tail of the other, right? So that their ends are connected to the different potentials. So I will take this, and then take this, connect it to one end of the battery, and connect this to the other end of the battery, so that they will be, both ends will be at a potential of what? V. Now, one of the things you should note in the arrangement, in series arrangement, is that when capacitors are arranged in series, number 1 thing is that the potential difference across each capacitor is different. The potential difference across each capacitor is what? Different. V for each is different. So that is one thing you should know. Then number 2 is that when capacitors are arranged in series, the charge across each capacitor is the same. So the charge for each is the same. So the charge for each is the same. So in that case, it simply means that the potential difference in this first capacitor is going to be V1. The potential difference in this second capacitor is going to be what? V2. So that our total potential V is going to be the sum of V1 and what? V2. While you understand that Q, the charge flowing through C1 and C2, is what? The same. Now let's get our total potential difference. Our total potential difference is V, which is V1 plus V2. So this is what we have. Now, if you recall the formula for capacitance, we mentioned that Q is equal to CV, right? So if I call this Q, which is the total charge, then it means I will call this the total capacitance, right? So that V becomes like my total voltage. Also, we can have Q again equals what? Equals C1 V1 for this particular case. Remember, the charge is still the same, so that's why I'm not saying Q1, I'm still saying Q equals C1 V1. Then for this, I would have that Q is equal to C2 V2. The charge is still the same. So if I substitute these three things into this formula in this fashion, I would have, where should I rub now? Okay, I think I will just rub this, so bear with me. Now, if I make V the subject from this first one, I have that V is equal to Q divided by QC equivalent. So I'm going to do the substitution into this particular formula. So I will replace this V with Q over what now? C equivalent. So I would have Q by C equivalent equals, if I do the same thing, V1 is actually going to be Q by C1, then plus V2 is going to be Q by what now? C2. So this is what I would have. Now if you notice, you would see that the charge is constant. So I would have that Q divided by C equivalent. If I factorize this charge, I would have Q outside equals what? 1 by C1 plus 1 by C2. So this is what I would have. Now if you watch, you would observe that this can now fizzle this, so that at the end of the day, you then have that 1 over C equivalent equals 1 over C1 plus 1 over C2. And if you have so many capacitors arranged in series, then you have 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C, and depending on how many you have, you can always use this sum to get them, right? I believe this is very clear to you. Now take note, the arrangement, the formula for finding equivalent capacitance is the direct opposite for that of resistors. Now, arrangement of capacitors in series, the equivalent is the reciprocal, right? Not the direct addition. So take note of that. This is the formula for finding equivalent capacitance of series arrangement. So take note of this. This is series arrangement, which is actually the opposite for resistors, right? Now, one of the points you should note from here is that the equivalent capacitance for series arrangement is always going to be smaller than each of the individual capacitance. The equivalent capacitance for series arrangement is always going to be smaller than each of the individual capacitance. I believe that is clear to you. What we mean is that if I have, say, C1 equals 2 farad, and then C2 equals 3 farad, then you want to find the equivalent capacitance. The equivalent capacitance must be smaller than both 2 or 3. So the value you will get here will be less than 2, and it will also be less than 3. That is what we mean. The equivalent capacitance of a series arrangement would always be less than each of the individual capacitance, right? So I'm going to solve this so that you can understand the concept. So we want to find the equivalent capacitance here so that you can get that point. So it's going to be 1 over C equivalent equals 1 over C1, which is 2, plus 1 over C2, which is what? 3. So that if I solve, I have 1 over C equivalent equals, my LCM here is what? 6. Thank you. 2 in this is what? 3. 3 times 1, 3, plus 3 in 6 is 2. 2 times 1 is 2. So I have 5 divided by 6, right? So that my equivalent finally, remember this is 1 over C equivalent, don't forget. 1 over C equivalent is 5 over 6. So that only C equivalent becomes the reverse, which is now 6 divided by 5. So if you divide this, 6 divided by 5. 6 divided by 5 is going to give me 1.2 farad. So what did you observe? Very correct. You observe that the equivalent, which is 1.2, is smaller than 2 and is also smaller than what? 3. So take note of this point. It's very important. Now, a second point I want you to also take note of is that if you have only 2 capacitors, only 2 arranged in series, and you don't want to go through this process, there's another short way for you to find the equivalent capacitance. So what will I do? I have only 2 capacitors. So what will I do? I'm going to simply do the equivalent is going to be the product over the what? Sum. If you have only 2 capacitors. Now let's do that so that we can verify. So now I have C1 and C2. So what would be their product? You are correct. Their product is going to be 2 times 3 divided by, what will be their sum? It's going to be 2 plus 3. And what do I have? I have 6 divided by 5, which is still what? 1.2 farad. So I believe this method is very straight to the point and very short for you to understand. Now, let's advance. Somebody might ask, we are talking about equivalent capacitance. What does it actually mean? I already explained by when you go to market to buy, you want an equivalent value that is different from those values you have, right? So an equivalent value is that value of capacitance that would give you, that would have the same effect as those capacitors you are combining. An equivalent capacitance is that capacitance that would have same effect as all other capacitors you are combining put together. That is equivalent, and that is what we have looked for. Now we want to do the second one here. So the second we want to consider is parallel arrangement of capacitors. Parallel arrangement. Parallel arrangement, right? Now, in parallel arrangement, capacitors are arranged in parallel when the heads are connected together to one end of a battery, and then the tails are connected together to another end of the battery. Then you say those capacitors are connected in what? Parallel. Now let me give the diagrammatical illustration. So say I have 2 capacitors like this. This is C1. Then I have another one like this. This is C2. This is the head here. This is the head. This is the tail, right? Now these 2 capacitors are connected in parallel. If I join these ends together to a common potential, and then I join these tails together to a common potential, so I would have something like this. So if I do this, it simply means that I have connected these capacitors in what? Parallel. Thank you. And this is the potential difference across them. Now, what is one of the points you should note for parallel arrangement of capacitors? For parallel arrangement, 1, the potential difference V is the same for each capacitor. The potential difference is the same for each capacitor. What does it mean? It means that the voltage you have here, V, is same voltage you have here, V. Same voltage you have here, V. So the potential difference, the voltage is same for parallel arrangement. Then number 2, the charge is different. The charge is different for each capacitor. The charge is different except in a case where the value of the capacitance are equal. But otherwise, the charge is always considered to be what? Different. Now, what this simply means is that if the total charge coming from here is Q, and when this charge gets to this junction, it will split, and you will have Q2 entering here, and then you have Q1 entering here, right? So that the total charge at this junction, Q is going to be Q1 plus what? Q2. Thank you. So if we do that, we're going to have that the total charge Q is going to be Q1 plus what? Q2. This is the total charge in this arrangement or in this system. Now, you also recall the formula for capacitance. You also recall that Q is what? CV. That is to say, the total charge is the total capacitance times the total voltage, right? So that also you can say that Q1 is actually C1 times V, since the voltage is the same. Also, you can say that Q2 is what? C2 times V, since the voltage is still the same. Now, if I substitute these three things into this particular equation, I will then have that Q is what now? C equivalent times V, right? Equals Q1, which is what? C1V plus Q2, which is what? C2V. Now, if you watch, something is common on this side, which is V. So I have C equivalent times V equals, what is common here? V. So I would factorize, and then I would have C1 plus C2. So what would you observe here? You observe that V can fizzle V. And then finally you have that C equivalent equals what? C1 plus C2. So this is how you can find the equivalent capacitance for capacitors that are arranged in what? Parallel. Now you still take note that this is actually the arrangement in series for resistors. So take notes. The circuit arrangement for parallel capacitors and parallel resistor is the same. The diagram is the same, but the formula is what differentiates both of them. So don't mix the concept. So this is equivalent arrangement for capacitors, right, in parallel. Now, one of the things, if we have more capacitors, you can simply generalize to the C1, C2, up till Cn, depending on how many you have. Now, one of the points you should take home from this is that the equivalent capacitance in parallel arrangement is always going to be bigger than each of the individual capacitors. The equivalent for parallel arrangement will be bigger than each of the individual capacitors. Now, what do I mean by this statement? What I mean is, say you have two capacitors, C1 equals 2 farad and then C2 equals 3 farad. And these two capacitors are arranged in parallel. They want you to find the equivalent capacitance. Since both of them are arranged in parallel, simply means that our equivalent is going to be their direct addition, right? So which is going to be 2 plus 3, and this will give me what? 5 farad. Now, if you take note, you would observe that 5, which is the equivalent, is bigger than 2. And 5 is also bigger than what? 3. So what it means is that for parallel arrangement of capacitor, their equivalent is bigger than each of the individual capacitance. Now, you will see problems like this in exam, and you will not need to solve. An exam problem can ask you, he said, they will say, in which way can two capacitors be arranged so that their equivalent is larger than each of them? So with this, you don't need to know values, but to understand the concept behind this, right? I believe this concept is very clear to you, and the take home for this is that you have two basic arrangement of capacitors, right? We have the series arrangement, where we mentioned that in series arrangement, the potential difference is different for each capacitor, but then the charge flowing through each capacitor is what? The same. Then we mentioned the second arrangement, which is parallel arrangement, that for parallel arrangement, the potential difference is the same, while the charge flowing through each capacitor is what? Different. So this concept should be very clear to you. Now, if you have watched my video up till this point, please do well to subscribe to my channel, like my videos, and then comment also share with your friends so that they can also benefit from this. Remember, this is prime concept. In my next video, I'll be solving example under the arrangement of capacitors. Thank you.